Hello students. Last class we have discussed about flow through convergent divergent nozzle, and we have seen how the fully expanded supersonic flow is established in a convergent divergent nozzle. And today's lecture will be covering supersonic inlet and its requirements, challenges, and problem with the supersonic inlet starting problem, and the different modes of inlet supersonic inlet operations will be covering in this lecture. Okay, we'll start with requirements of supersonic inlet. It all depends on where it is applied. And turbojet engine moving with supersonic speed or ramjet scramjet engines. So turbojet engines moving with a supersonic speed has got a constraint. So here the flow has to be decelerated to a low subsonic, say around Mach 0.4, only then it can be admitted into the compressor. Whereas in the case of ramjet or scramjet engine, there is no such constraints. Because there is no compressor, you can handle even supersonic flow with a slight modification in the combustor. So our focus will be designing a supersonic inlet. The challenge of designing supersonic inlet is, so we need to decelerate the supersonic flow to a subsonic speed acceptable by existing compressor. This is the challenge. So what we have option. So going for a reverse nozzle diffuser is an option. So we already discussed a supersonic nozzle, that is convergent divergent nozzle, where you can say the Mach number at the entry will be subsonic and it passes through the convergent section and then followed by a divergent section resulting in supersonic flow, Mach number greater than 1. This is a CD nozzle. And when you try the same concept, if you place this CD nozzle in the reverse order, reverse nozzle diffuser, where the entry Mach number will be supersonic and the exit Mach number will be low subsonic. And if you put it in the reverse manner, our purpose could be solved, because we need to decelerate the flow from high supersonic to low subsonic. This is the requirement. When you try this, we have a problem associated with this. So we have a problem of shock interaction with the boundary layer, flow instability, violent oscillation. All these issues will be occurring when you try this option. Let us see how you can find the solution for this. So when you start with a supersonic inlet, whenever you are dealing with the supersonic flow, the presence of shock we cannot avoid. So here we need to find out an option where we need to establish a shock system with minimum pressure losses, and that is the requirement now. And this process of establishing a stable shock system is referred as a starting of an intake. So we are going to discuss how a stable shock system could be established in the process of decelerating the flow from high supersonic to low subsonic. Let us see how it is done. Here, the starting problem of intake could be explained with a series of diagrams. And you can start with the diagram A, where you can see here entry Mach number is lesser than 1, or so low subsonic, and it enters to the convergent divergent section. As we discussed, it's like a reverse nozzle diffuser. We will have a convergent section followed by a divergent section. So here AA is the capture area, AI is the inlet area of the intake system, AT is the throat area, and AE is the exit area of the intake system. Here entry Mach number will be, so we will start with a lower Mach number, a lower speed, so let us say around 0.3, and it enters into the intake system, and at the entry of your inlet it's still in a subsonic mode, and then it enters to the convergence section. So when the subsonic flow is passing through the convergence section, it gets accelerated and it tries to achieve a higher Mach number. But at the throat, let us say it is still under subsonic flow, and it is it is flowing through the divergence section. When it flows through the divergence section, say still it is in a subsonic region, and the subsonic flow is passing through the divergence section, So it will act as a subsonic diffuser. That means flow will be decelerated further, and at the exit of the intake system, we will still have a subsonic flow. So this is a simple case. Now we are accelerating the flow to a high subsonic case. Still it is subsonic, but we can say the Mach number will be 0.6 now. At this flow, and still at the entry of your intake system, Mach number is less than 1, subsonic still, and when it is passing through the convergence section, it will try to accelerate and it will try to achieve the critical condition. Okay, flow is accelerating now and it is approaching Mach number closer to 1, that is the choking condition. And in this condition, a Mach number once it is reaching closer to 1, it is attaining a choking condition, that is the maximum mass flow condition achieved. For that, there is a relation connecting area ratio and the Mach number, and AA by AT, and the Mach number is given here. And remember, AA is the capture area, and this AA by AT, AT is the throat area. AA by AT is will be for a high subsonic value. When you increase the Mach number, free stream Mach number higher value to a higher value, and your AA by AT should be lesser than AI by AT. So AI is the inlet area. So AA is a capture area. The capture area is shrinking, we can say now. AA by AT will be lesser than AI by AT. AI is the inlet area, AA is a capture area. When you accelerate the flow to a higher Mach number, so the capture area is shrinking. When capture area is shrinking, so there will be more spillage. When spillage is occurring, that leads to a nozzle drag. So when you increase the Mach number to a higher value, say Mach number closer to 1 now, and the area, I said now, the capture area will be reduced, compressed, we can say. When the flow is compressed here and it gets pressurized, and the flow gets pressurized, and there will be a pressure rise here, and this result in a sort of weak shock. So the weak shock will be formed head of your area AI, you can say, inlet to the entry to the inlet intake system. And since the Mach number at the entry is closer to 1, the shock formed, the pressure wave created here will be of weak in nature. So once the shock is formed, the downstream side of the shock will have a subsonic flow. So flow is decelerated now through a shock system, and now it becomes a subsonic flow, and at entry it becomes subsonic. So the regular manner it is accelerating now from subsonic to sonic, and then it is again subsonic when it passes through the diverging section. So when you increase the Mach number further, you can say you are increasing the Mach number higher than 1. Say, let us say it is 1.5 now, and 1.5 or little higher also. At this Mach number, as I said now, the capture area, as you increase the Mach number at the entry, capture area is shrinking further. So it is compressing, the flow is getting compressed, and the pressure wave will be created, and this result in a strong shock. This is something like a bow shock, which is again, it is similar to your normal shock. So it result in strong shock. The downstream side of your shock, again flow becomes a subsonic. So when the strong shock occurs ahead of your inlet, you can see that the capture area is already smaller, and there will be more spillage occurring. That result in nozzle drag, and the flow becomes subsonic. And due to this strong shock present head of your intake system, the flow there will be a stagnation pressure losses. Whenever you have a strong shock happening, there will be a stagnation pressure loss. Static pressure will be rising, and there will be a stagnation pressure loss. stagnation, when stagnation pressure loss is occurring, you can see flow becomes subsonic and there is a drop in stagnation pressure. We are losing the energy, kinetic energy available in the flow. So you can remember the choking condition is decided by the free stream conditions here. Your P naught, T naught decides your choking condition, or you can say the mass flow. We already discussed mass flow equation in terms of P naught, T naught. When P naught is the stagnation pressure, and the P naught is dropped or decreased due to the presence of strong shock here. It affects the mass flow also. Even though the Mach number reaches closer to 1 here, because of the lower P naught value, you are result in low mass flow here. So mass flow will be affected and there will be more spillage that will result in shocks. So we need to avoid these shocks. Let us see how it could be done. So now the Mach number is higher, but when you increase the high Mach number, there is a presence of shock we cannot avoid, and these shocks can be pushed towards the inlet. Okay, the flow is accelerated further and it is closer. You are bringing the velocity closer to the design value, and see that when you are increasing the Mach number, free stream Mach number, the shock formation will be there, and the shock can be brought closer to the entry of your intake system. So Mach number closer to the design value, and you are increasing the Mach number closer to the design value, and see that the shock is just ahead of your entry to the system. It is almost at the lip of your intake entry, you can say. Still, this is not advisable because this is again a strong shock. The phenomena is same, the flow is getting compressed and will result in a strong shock, high pressure wave, high pressure rise, and there will be a stagnation pressure losses occurring here. And when the stagnation pressure loss is occurring, then it results in mass flow. It will be reduced mass flow again. There will be more spillage again occurring, and this also should be avoided. The moment you see this situation where the strong shock is just at the lip of your entry, and you have to momentarily speed up your system. So we have to increase the, you can say it's a overspeeding. We need to do a overspeeding so that the shock can be pushed inside the intake system. Momentarily it should be done. So you have a design Mach number value, and momentarily you need to speed up your system so that we are doing a overspeeding and the shock will be pushed further down. When it comes, so this is the MO stands for overspeeding. Mach number, overspeeding Mach number slightly higher than the design value, and when you do this, when you speed up the system to overspeeding the system, then we can say the shock will be pushed inside. And remember, shock cannot stay here at the convergence section. It will be pushed further down. So it may stay at the diverging section. Remember, till shock is formed, the flow will be supersonic. So you are not dropping, or you are not losing any kinetic energy here up to this point. We can see the flow is still supersonic. So we got all kinetic energy available, and when it forms the shock here, and remember, when the supersonic flow is passing through the convergence section, flow gets decelerated. So slowly the high supersonic flow will be coming to a sonic flow, or when it is passing through the divergence section, again it becomes supersonic, but it will be low supersonic, we can say. When the low supersonic wave is passing through the divergence section, we may have a shock here. Again, it's a sort of normal shock. There will be a pressure losses, stagnation pressure loss. Compared to the previous case where the normal shock occurs at the lip of your entry, where it will be very strong shock resulting higher pressure loss, higher stagnation pressure losses. Whereas here, the stagnation pressure loss will be occurring, but it is relatively lower. So our purpose will be solved now. The flow becomes subsonic with the marginal losses. We can convert the high supersonic flow into a low subsonic flow. But this is done with the overspeeding option. But instead of keeping your shock wave on the divergence section, and if you carefully control it and make sure that the shock occurs exactly at the throat or nearer to the throat, and by adjusting the flow to the design Mach number, so you can make this shock occurring exactly at the throat or closer to the throat. The advantage of doing so is, so up to throat the flow is supersonic. We are not losing uh, any kinetic energy here, and if the capture area, if you look at, it is same as your AI. So the entire inlet area is admitting the flow, the mass flow is not affected, and there is no spillage losses is also minimum, and flow is supersonic here. And when it approaches throat, it is closer to 1, and even if shock occurs here, this will be of weak shock. That means the stagnation pressure loss will be minimum here, and then once it goes through the divergence section, it becomes subsonic. So we could achieve the decelerating high supersonic flow to a low subsonic flow through a normal shock, that to a weak shock forming at the throat section. So you have to carefully do this, so that once you establish this system and we are able to successfully convert your supersonic flow into a subsonic flow with minimum losses, you have to position your normal shock or weak shock nearer to the throat section. Then it will be possible to have a low subsonic flow at the exit. So this is done with the overspeeding option, and this mechanism we call it as a shock swallowing option. So this shock swallowing option is done with the overspeeding. There is another option we have. Say moving this strong shock inside the pushing the strong shock inside the convergent divergence section is can be done with the varying throat section, throat area also. By suddenly increasing the throat area, we can push the strong shock inside your CD section, CD intake systems, convergent divergence section, or and we can have a weak normal shock occurring section closer to the throat. This way also we can obtain varying throat area. By varying throat area also, shock swallowing can be done. So this way also we can establish a weak shock system inside the intake system, so that with minimum losses you can convert the high supersonic to a low subsonic cases. This is handling the shock system inside the intake system. So we have seen how a stable shock system is established inside the intakes, supersonic intake system, and flow is decelerated from high supersonic to low subsonic. And the same thing can be done with the external deceleration also. Here, external deceleration or compression method also can lead to decelerating the flow from high supersonic to subsonic. And here, this is done through a series of oblique shocks followed by a normal shock. For this to occur, we need to go for a center body. As a conical shaped center body will be placed inside your intake system. So it will be, this is the center body, and it's a conical shape point-edge center body will be protruding from your intake system. And here, when the fast moving free stream, high supersonic free stream is approaching the center body, and there will be a oblique shock formed here. So based on the ramp angle and the ramp angle, you can say the strength of the oblique shock form will be deviating. So if you carefully design your center body, like say you can have a number of steps formed, so that whenever the free stream flow is hitting the steps, then there will be a oblique shock originating from that. So when flow is passed through the oblique shock, there will be a reduction in velocity, reduction in Mach number, and corresponding stagnation pressure losses also will be occurring. Remember, compared to the normal shock, when the flow is passed through the oblique shock, the stagnation pressure loss will be relatively lower. So this concept is tried here. So let us explain this, how the flow, supersonic flow is decelerated to subsonic flow through a oblique shock. So for illustration, I have taken 3 steps. You can see the center body has got 3 steps. So 3 oblique shocks will be originating, and through each oblique shock, flow is decelerated to subsequent lower Mach number. Finally, it is end up with a normal shock where the flow is decelerated further to a subsonic case. Let us see, there is a center body with 3 different steps. When the approaching Mach number, let us say it is 3, and when this free stream flow with the Mach number 3 hits the first ramp, so there will be oblique shock formed, and the Mach number will be reduced from 3 to 2.26. So corresponding stagnation pressure loss also will be there, and the pressure ratio obtained, let us say it is the P02 by P0. 1 is the entry and 2 is the downstream side of the first oblique shock. The P2 by P1, the stagnation pressure ratio is given by 0.895. That means it's about 10% pressure loss is observed here through the first oblique shock. When the flow is further moving down, and it's the second step here. So again there will be a oblique shock formed. Flow is decelerated further from 2.26 to 1.65. The Mach number will be decelerated. Mach number will be reduced. So flow gets decelerated. The corresponding pressure ratio is noted as say 0.945 P03 by P02. So here about 5% stagnation pressure loss is observed. Again, it's moving further down, so it's the third ramp where the Mach number is reduced from 1.65 to closer to 1. So there will be 3 steps. The flow will be decelerated from high supersonic, say Mach number 3 to Mach number 1 in 3 steps. So each steps there will be a deceleration of flow and through oblique shock, and flow gets closer to Mach number 1, and then we will have a normal shock. So when it passes the normal shock, you have to adjust your normal shock so that it forms nearer to the lip of your intake. So this can be done by carefully designing your ramp angle, the center body and its ramp angle. If you design it correctly, we can position your normal shock closer to the lip, so that normal shock will be formed nearer to the lip of your intake system, so that, and when it passes to the normal shock, which is a weak normal shock, Mach number can be reduced to, say, from 1 to 0.67 it can be reduced. And when it moves further down, so this inflect section will be of diverging section, so flow gets decelerated further, and it attains the Mach number closer to 0.4, which is our requirement. So subsonic flow, it will be decelerated to subsonic flow. And if you look at the deceleration occurring here, and through each oblique shock, so we got a pressure losses, stagnation pressure loss. The first case it is 10%, second case is about 5%, in third case it is about 15%. And if you put together all, the overall pressure ratio will be coming around 0.735 and accounting 25% of loss, roughly it's about 25% stagnation pressure loss is occurring. So it is reasonably good. And if you try to have the same thing with a normal shock, imagine instead of reducing the flow, decelerating the flow from high supersonic to low subsonic through a series of oblique shock, if you are trying to do with a normal shock, imagine instead of conical center body or sharp edge center body, we need to go for a blunt body. Imagine it is replaced by a blunt body, which is resulting in a normal shock. When normal shock is occurring, the flow will be the pressure ratio, if you look at, it will be reduced to a pressure ratio obtained will be 0.33. That means it's accounting about 65% pressure stagnation pressure loss. So this is not advisable again. So if you want to have a decelerated flow from high supersonic to subsonic, and we need to go for a series of oblique shocks. So this can be done by carefully designing your center body. And imagine if the steps I said, the steps are infinite number of steps if you are having, and the flow will be decelerated in a smooth manner, and the stagnation pressure loss obtained also will be very marginal, or you can say it can be brought down to 5 to 10%. And if you imagine, if you form infinite number of oblique shock, pressure loss, stagnation pressure loss obtained will be almost nil, so that the flow can be decelerated to subsonic flow. This is how flow can be decelerated externally to get externally when with the center body protruding from the intake system. So based on the shock position, the inlet operation can be classified as a subcritical mode, or supercritical mode, or critical mode, you can say. If the all shocks, oblique shock and normal shock formed are outside the entry of your intake, and we call it as a subcritical mode of operation. And if the oblique shocks formed are outside the external to the intake, and the normal shock formed will be at the exactly at the lip of your entry, then we call it as a critical mode of intake of supersonic intake operation. And if the normal shock formed will be if it is swallowed inside the intake system, and then we call it as a supercritical mode of intake performance. So based on your shock position, we can have a different intake modes of operations. Okay, we are going to wind up this section. Before winding up, let me summarize what you have seen now. We started with the intake requirements of supersonic intakes and the challenges it faced. So decelerating the flow from high supersonic to low subsonic through a stable shock system. Internally we can manage, that is starting problem we have discussed, and then externally deceleration, external compression mode also we can try and obtain the deceleration of flow from high supersonic to low subsonic, giving different modes of inlet operations. So with this we'll wind up this lecture. Thank you all. Thank you for watching.